I will start with same problem. Okay, draw asymptotic bode plot for the given control system. G of s equal to 100s s plus 10. So we started with the conversion of what is that bode form. So how can we convert the given transfer function into bode form? So if it is s plus a, then it should be converted as a into 1 plus s divided by a. Okay, so you take constant a outside, then automatically 1 plus s by a will come, and like we have to do the process for g of s, and after getting the bode form, and we will get three terms, especially in this problem. There is a term constant and differential function and simple pole function. Okay? Right. So we have to draw the asymptotic bode plot for each term, term 1, 2, and 3. And finally, we have to find out the bode magnitude and as well as first plot. So to start with, you take 20 log of 10 because this is your first term. I mean, 10 is your first term and it is a constant. So if you are converting the given value into dB, then 20 log 10 is equal to what is that? 20 dB. Okay, so to convert the magnitude into gain in dB and take 20 log of that particular magnitude, then it will give uh, what is that? The gain in dB. So we are getting 20 dB because this is log base 10. So 20 log base 10 and here is 10, and as per logarithmic rule, 20 into 1 will be the answer and it will be 20 dB. Okay. So we are trying to plot the what is that bode magnitude plot. Okay. For that, I'm going to draw the magnitude plot. Okay. And this is omega. This is gain in dB. 0 dB, 20, and plus 40, minus 20, minus 40 dB. Okay. So this may be 0.1, 1, 10, 10, 100, 1000 will go like this. So if you're talking about the magnitude plot of what is that? The simple gain, and it will be like this. Okay. So magnitude plot of what is that? The gain B. This is 20 of 10. Okay. Now we can draw the magnitude plot of what is that? A second function, which is a differential function. So if you're talking about the differential function, then it can be the second term is a differential function. Yes, it can be written as 1 plus s divided by 1. Okay. So what will happen? And this is your reference. This is your reference pole. And if you're talking about this, what is that? 1. And if you're multiplying this frequency, the next will be 10, and another will be 100. Then it will go like this. So if we are trying to draw this, then it will be okay. So this is your second term. Okay, so this is your first term. This is your second term. Am I right? So this procedure already we discussed in the previous class. Okay, so we were trying to draw the bode magnitude and as well as first plot for the different terms which are available in the control system. So this is the magnitude plot. Okay, this is magnitude plot of 2, and this is magnitude plot of what is that? The function 1. The next will be the third function. It is 1 divided by, third function is 1 divided by 1 plus s by 10. 1 plus s by 10. Am I right? So this is integral function, because integral function, and as well as what is that? It is nothing but a simple pole. Okay, it is also called as a simple pole, and if 1 plus s divided by 10, then it will be approximated as s by 10. So this is called integral function. Integral function. Where now here you see that this frequency is 10. Okay, so you mark 10 here. Okay, so mark 10, and next frequency will be uh, 10 into what is that? 10 into 100. Okay, the next one will be 100 into 10 equal to what is that? 1000. So like it will go. So what will happen? This is 1 plus. Am I right? So starts from here. It goes like this. Okay, so this is third term. Okay, magnitude plot of third term. Magnitude plot of third term. Am I right? Right. Now we got three different magnitude plot for the given transfer function. Now we have to find out, or we have to combine, what is that? All the three plots. Okay, so it will give what is that? The magnitude plot of the given system. You see that this is one corner frequency and 10. Okay, so there are three regions: region 1, and region 2, or you can call it as region A, and region B, and this is region C. Okay, so what region A? What will be the slope changes? You see that this is 0 dB. This is 0 dB per decade, and this is plus 20 dB per decade, and this is minus 20 dB per decade. Okay, so this is called a slope. It's called a slope. Am I right? So slope for straight line is 0 dB per decade, and for differential function, and it will be 20 dB per decade, and for integral function it is minus 20 dB per decade. So at region A, okay, so what are the slopes? 0 dB plus, once again, and this is also what is that? 0 dB per decade, okay, plus 0, and here what is the dB? Plus 20, plus 20 dB per decade. So if you're adding together, then it will be 20 dB per decade. Adding together, it will be 20 dB per decade. So up to this portion, okay, up to this portion, okay, slope is not changing. So it will be 20 dB per decade. Okay, now I can say, okay, so this is your part to this. Okay, slope is not at all changing. Okay, even with B, you can see. Okay, so in B portion also, you can see in B, what are the slope changes? You see that this is okay, and this is A, and this is B, and this is C. Am I right? Slope at A, 0 dB plus slope at B, it is 20 dB, and slope at C, it is 0. So it is nothing but 20 dB per decade, 20 dB per decade. So up to corner frequency 10, so okay, uniform slope will be there. Am I right? Then consider third portion C. Okay, so at C you can say this is portion A, and this is mm, portion B, and this is portion C. Am I right? So portion A at 20 dB per decade, and portion B 0 dB per decade, and portion C minus 20 dB per decade. So what will be the total change in slope? It will be 0 dB per decade. 0 dB per decade. Then what will be the, okay, what will be the what is that magnitude plot? So it will go like this. It will go like this. Am I right? So this is your what is that magnitude plot. This is your magnitude plot. Magnitude plot of GFS. Okay, so this is approximation. This is the approximation and approximated plot. But further we have to do approximation. So how can we do this? And you see that, okay, so maybe, and this is your exact magnitude plot. So it's being asymptotic magnitude plot. After drawing this, the green color highlighted line, then parallelly you have to draw what is that a line which what is that the highlighted line. Am I right? So this is your magnitude plot of GFS, and we got this magnitude plot because of assumption. Am I right? So the first portion is over. Then second portion is your phase plot. Okay, so phase plot drawn between phase angle in degree versus what is that log omega scale or omega log omega scale. So this will be 90 degree, and this will be 180 degree, and 0 degree, minus 90 degree, minus 180 degree. Am I right? Then it will be 0.1, 1, 10, 10 power 2, and this will be 10 power. Okay, same scaling should be followed with respect to x-axis. So x-axis always it is representing what is that log omega or frequency. Now, as I said, there are three terms. Am I right? So there are three terms in phase plot also. Phase plot. Okay, so what are the three terms? First term is a 10, and second s, and third term is 1 by 1 plus s by 10. Am I right? So what will be the phase plot for the constant? What will be the phase plot for the constant? So if you are talking about phase plot for the constant, and it will be plus 90 degrees. Am I right? So it will be plus 90 degrees. So it will be like this. This is the phase plot of portion of 1. Okay, phase plot of portion of 1. The next term is, what is that? S. Okay, so S can be found like this: 0 plus S by 1. Okay, so here we have to do approximation, and it will be, uh, 1 by T. Okay, and the T, and okay, like T by am I right? Okay. And 10 by T. So because it should be multiplied by 10. It should be multiplied by 10. Okay, so 10 by T, 1 by T, like we have to do it. So this is the assumption. So here we are doing some assumption here. If your frequency is 1, then it should be splitted like this. So how can we split this? Find 1 by T and 1 by T and 10 by T. Each frequency is multiplied by 10. Okay, so we are taking some reference. Okay, one reference frequency less than 1, and we are taking one reference frequency higher than 1. Okay, that's the point. Okay, so remember this before plotting the what is that first plot. So this is a second case. Okay, so second case is a differentiator. Am I right? So this is a differentiator. So what we are going to do here, differentiator curve, and actual frequency is 1. Frequency is 1, and the 1 divided by t will be here. Okay, 1 divided by t will be here, and 0.1 t divided by 0.1 divided by t will be there. Okay, then we can able to draw like this. 1 minute. Be online. Yeah, 1 minute. I made a mistake here. That first plot for the first part. Okay, it is nothing but 0 degree. Am I right? So it's 0 degree. Okay, so this is your first term, and the 90 degree for the second term. Okay, 90 degree for the second term, and 90 degree for the second term, and this procedure should be followed for the what is that? A simple pole or a simple zero. It should not be followed for what is that? A simple differentiator. So you try to follow this, okay? Follow this rule to the what is that? Simple pole, and one it will be 1 plus s by 10. Then it will be what is that? Point 1 by t and 1 by t, 10 by t procedure can be followed here. Okay. So what will happen? Simply try to understand if you are projecting a simple constant to the first plot. Okay, so it will give 0 degree. Am I right? It will give a 0 degree. Okay. Then if you are projecting a simple what is that differentiator, you will get what is that 90 degree. Am I right? Then if you are projecting a simple what is that? A simple pole. Okay, so you will get a what is that? And what is that? You will get some negative slope occur. You will get some negative slope occur. Okay, all right. So here the frequency is 10. Here the frequency is 10. Okay, so if frequency is 10, okay. So what will happen? And this is your frequency 10. This is your frequency 10. Then you can able to draw. Here, okay, and we have to take we have to put some assumption here. Okay, so 10 by 10 is equal to, so curve should start from here, and 10 should be multiplied by 10, and it will be 100. Okay, so this is the assumption for a third term. So what will happen? It will go like this. Okay, so if you're taking a curve like this, you see that it is crossing the next frequency at an angle of approximately at an angle of 45 degree, at an angle of 45 degree. So like it will go. So this is the curve, first plot for what is that, the third term. Okay, so here it is 0 degree per decade, and here also 0 degree per decade. Okay, and here it is minus 45 degree per decade, minus 45 degree per decade. Okay, so try to understand. Okay, the first one, if you are projecting a constant to face plot, it will exactly appear at the origin. And second one, we are projecting a differential function into the face plot. Okay, yes, it is a straight line because we are getting 90 degree angle. Then we are projecting a what is that? A simple pole into the face plot. Okay, if we are projecting simple pole into the face plot, then we have to follow this rule. What is the rule behind it? What is the frequency here? It is 10. What is this? This is a 10 here. Okay, so you please simply what is that? You do simply divide by 10, then you will get 1 radians per second. Then in the next step, you multiply 10 with 10, then you will get 100 radians per a second. Okay, so mark all those points, then you project the line, then you project the line. Okay, so what will happen? It will cross the 10 at an angle of minus 45 degree, and it will cross 100 at an angle of what is that, 95 degree. So from one frequency to another frequency, from 1 to 10, what will be the slope? It is minus 45 degree per decade. Minus 45 degree per decade. Okay, so try to understand this. Now we have to combine all these plots. Okay, right. As I said, there are three portions. Okay, so here can okay, here is so this is your portion A, and this is your portion B. Okay, so this is your portion B, and this is your portion C. Okay, your portion C. Okay, right. Now at A, you add all the what is that degree per decade. So what will happen? Here it's a 0 degree per decade, and here a 0 degree per decade. Am I right? So the curve will be so up to one. The curve up to one curve will be like this because there is no change in slope. Am I right? So here it is 0 degree per decade and 0 degree per decade here. Okay. So if you're adding, the cumulatively you will get a 0 degree per decade. Right. And next is okay. So there is a change in what is that slope here. You see that, and here it is a 0 degree per decade. Right? 0 degree per decade. Okay, and you know mm, and here this is 45 degree per decade, 45 degree per decade. Am I right? Okay, so what will happen? That curve will be like this. Then during the C period, okay, you see that simply it will follow. um, okay, so here another another decade will be there. Another this is your this is your the next level of phase plot. Okay, so what will happen from here? It will go on like this. Am I right? So this is your phase plot. This is your phase plot, and once again the phase plot can be further modified like this based upon the assumption. Okay, so this is your phase plot. This is your phase plot. Okay, so this is asymptotic board plot, and this is the method to draw your asymptotic board plot. Okay, so if you have any doubt, then you can discuss with me. Is there any doubt in this? Is there any doubt? Okay, so try to understand. The first step is converting the given form into board form and separate into three different okay, three different points. Okay, first one is constant, differential, and simple pole, and try to find out what is that the magnitude plot, and the second one is the phase plot. Okay, so, right, we can go to next problem, and this is second type of problem. The sketch uh, board diagram of G of S 1 divided by S square plus 201 S plus 200. Am I right? Okay. So solution for this. So G of S equal to 1 divided by S square plus 201 S plus 200. So here we are getting a quadratic equation. So we have to solve this. Okay. So if you are trying to solve this, then you will get an answer like this: 1 divided by S plus 1 into S plus 200. Okay, then convert into board form. Board. The board form will be G of S equal to 1 divided by S, and take 200 outside, then it will be 1 plus S divided by 200. Right. So this can be written as G of S equal to 1 divided by 200, 1 plus S into 1 plus S divided by 200. Okay. So here we can separate 1 divided by 200 into 1 divided by 1 plus S into 1 divided by 1 plus S divided by 200. Okay, so these are the three terms. This is term 1, and this is term 2, and this is term 3. Okay, so this is constant, and this is a simple pole, and this is also simple pole. Okay, so first we have to separate the what is that, all the three functions. Okay, and we have to identify whether it's a constant, a pole, or a zero. Okay, so if you are getting a quadratic equation like this, then we have to separate it, or we have to find out roots of the quadratic equation, and based upon the roots of the quadratic equation, we can split the denominator, and after splitting the denominator, get your board form. After getting your board form, and you get the what is that, the terms which are available in your transfer function. So we identified there are three terms for this particular G of S. Right. Now, 1 minute. Okay. Right. The first term is this, magnitude plot. Magnitude plot. Okay. So in that magnitude plot, the first term is 1 by 200. So convert this into dB, 20 log divided by 20 log 1 by divided by 200, and 20 log 1 minus 20 log 200. Okay, so this will be 0 and minus 20 log 200, and this will be approximately minus 46 dB. So use calculator and find out. Okay, so if you are getting if you are getting minus 20 log 200, and the answer for log 200, and it can be multiplied by 20. So after doing all this process, you are getting minus 46 dB. Okay. So we have to plot this. Okay, x-axis is log omega scale, is always representing frequencies, and this is y-axis, gain in dB, gain in dB. So here x-axis, at x-axis, gain is always 0 dB, here it is 20 dB, and here it is 40 dB, minus 20 dB, minus 40 dB per decade, and in this problem we are getting minus 46, so extend up to what is that, minus 60 degree, and here corner frequency is 0.11. Every frequency should be multiplied by 10. Okay, so if you are multiplying 0.1 with 10, you will get 1, and multiply 10 with 1, then you will get 10, and multiply 10 with 10, you will get 100, then 10 power 4. Okay, so this is the way to present your x and y axis in case of magnitude plot. Okay, so first we are trying to draw the magnitude plot of what is that, the constant 1 divided by 2. So this is your first term, and here the gain in dB is minus 46, minus 46. So 46 in the sense approximately like this. Okay, So this is your first term magnitude plot, and it is 20 log of 1 divided by 200. And here the change in, there is no change in slope, so it will be 0 dB per dk, 0 dB per dk. Am I right? Then the second term is 1 divided by 1 plus s. Am I right? So this can be written like this: 1 divided by 1 plus s divided by 1. So this one is your corner frequency, and you mark here. Okay, so you mark here, and here, you know, it is a simple pole. It is a simple pole. Okay, so you will get a diagram like this. Okay, so the 1 plus, okay, 1 plus, yes, okay, so that's the reason it is drawing like this. Then it will reach the next corner frequency at 20 dB per decade. The next corner frequency another 20 dB per decade. Oh, sorry. And this is, you know, this is what is that? 1 minute. Okay, so this is, you know, coming down, coming down, okay, because, you know, the change in slope is minus 20 dB per decade. So like this. So this is minus 20 dB per, because, you know, it's an integral function. Am I right? So if you're calculating integral function, and 1 plus s divided by 1. Am I right? Okay, if s is dominating, then this will be equal to s, and okay, 1 by s, and then this will be 1 by s. This is nothing but integral action. This is nothing but integral action. So during the integral action, you will get, you know, minus 20 dB per decade, and the starting frequency is 1. How we are finding this 1? Because at the denominator 1 is there. So one is your corner frequency, and we are getting this straight line because of 1 plus s. Okay, so if omega takes lesser value, this is, you know, for higher omega. If omega takes if omega takes, you know, less value, then 1 plus, 1 divided by 1 plus s is approximately equal to, what is that, 1. So this straight line is, you know, representing this one term. So it is very clear, and this is, you know, the second term magnitude plot. Second term magnitude plot. So what will be your third term? So third term will be 1 divided by 1 plus 1 plus s divided by 200. Okay, so here the corner frequency is 200. Okay, so where is the 200? This is 100, and this is 200. This is 200. Okay, so if you're talking about, you know, 200, and what will be the next frequency? Okay, 200 into 10, it will be next frequency, your next frequency. So like it will go. Am I right? Now we can able to plot the board magnitude plot for a third term. Okay, so it should be okay, from the origin, and here. Okay, so this is the corner. 200, and the next, you know, it will be 2000. It will be 2000 here, so it will be, so this is your third term magnitude plot, and here it is, you know, some minus 20 dB per 30, minus 20 dB per 30. Am I right? Okay, so we have drawn board magnitude plot of all the three functions. Now we have to combine. Now we have to combine. Okay, so up to this is portion A. Okay, and up to this portion B, and after this, B portion C. Okay, so at portion A you find the change in slope. At portion A, this is 0 dB per decade. Okay, and this is also 0 dB per decade. So if you're combining 0 plus 0 plus 0 equal to 0 dB. Am I right? So up to this, you will get same line. Then next, portion B, we're considering portion B, it is 0 plus, okay, 0 plus, okay, minus 20 dB per decade. Then it will be minus 20 dB per decade. At C, you can say, okay, at C, it will be minus 20 dB per decade, and minus 20, and it will be minus 40 dB per decade. Okay, so this is the condition. So this is the condition here. So now you can highlight bode plot. So up to what portions that, okay, so up to the here, up to here, okay, to here, to here, okay. Then after that, the slope will be, what is that, minus 40. Okay, so please keep this point. If it is minus 40, and it should reach the what is that, it should reach the next corner frequency. The next corner frequency is 2000. Okay, so where it have to reach, after 40 dB, after 40 dB, this is 46, and this is minus 80. Okay, 40 plus 46, it will be 76. So approximately like this. Okay. So this is minus 20 dB per decade to this portion. Okay, and here, and this will be minus 40 dB per decade. Okay, so this is the approximation, and before doing the approximation, then we have to go for what is that, the next final curve, and it will be like this. Okay, so this is your final board. This is your board plot. Okay, so this is an approximate board plot. That's the reason we are doing all this assumption. Okay, so that's all about the magnitude plot of the given function. Magnitude plot of the given function. Now we are going towards phase plot. Okay, so what is your phase plot here? So for that we have to do, what is that, a calculation. So phase plot, okay, for the three terms. So first term is 1 by 200, and second term is 1 divided by 1 plus s, and third term is 1 divided by 1 plus s divided by 200. Am I right? So if you are trying to draw the board plot of what is that, uh, 1 divided by 200, so it is a constant. So if you are talking about the constant, and it is exactly located at the uh, origin. Okay, so that's our finding. So okay, so this is your log omega scale, and this is magnitude 90 degree and 180 degree. Okay, and this is phase angle, and this is 0 degree, minus 90, and minus 180 degree, and here it is 0.1, 1, 10, okay, 100, okay, 10,000, and here, sorry, 1000, and 10,000. So every frequency should be multiplied by what is that? 10. Okay, so that's a prediction. And the first term is 100 by 200. So if you are finding first plot, it is exactly at the origin. Exactly at the origin. Okay. The next term is 1 by 1 plus s, and this is your integral function. Okay. So what is the frequency? 1 by 1 plus s, and here 1 by 1 will be there. So 1 is your frequency, and where is 1, and this is your 1. Am I right? And divided by 10, and this will be your the point, and the next into 10, and it will be your next point. Okay. Mm. Okay. Then the curve will be like this. 1 plus, it will be like this. Right. Going like this. Okay. All right. And this is dB here exactly at this, measuring the degree at this, it is crossing the next corner frequency at 1, and corresponding degree is 45 degree, minus 45 degree. Then change in slope will be minus 45 degree per decade through the line. Okay, so this is the second term, and this is your first term. The last term will be 1 by, what is that? S divided by 200. Okay, so 200 divided by 10, and it will be 20. 200 into 10, it will be 2000. So this is the approximation, and we have to start the phase plot 20 and end with 2000. So where is 20 here? And this is 20, and where is 2000, 1000, and here it will be 2000. So I will change the color because that we can able to understand clearly. So first plot, it will go up to the color frequency, and it will reach, yeah. Okay, so this is your what is that? Third first plot. This is your third first plot. So many portions are there. You can see up to this A, and up to this B. Sorry, not here and here. To this B, and this is portion C. Now we can combine all the three lines. Okay, so see that, and up to this, up to A, there is no change in dB per dk. There is no change in dB per dk. Am I right? Okay, so automatically what will happen? 1 minute, I will complete this class, because or otherwise there will not be any continuity. Like this. Okay. After this, you can see. Okay, so this is minus 45 degree, 45 degree, and this is also uh, and this is also minus 45 degree per decade. Okay, so minus 45 plus minus 45, it will be minus 90 degree, minus 90 degree. So what will happen? It will go further. Go further. Okay, so to finish the first plot, okay, so you can say. So the screen is your final, okay, final first plot. Okay, so that's all about magnitude and the first plot of the given transfer function. Okay, so you can able to understand this. If you have any queries, then you can discuss it. Okay. Thank you.
Sir, roll number 5 present.
Roll number 5. Uh,
5.
Sir, 15.
5 and 15 are present. Okay.
Sir, 16.
1 minute. 5, 15, and 16. Anybody else?
Sir, 19.
19 also present. That's all, na? Okay. Thank you, ma. Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Okay. Thank you.
Sir, roll number 7%.
Thank you, sir.
Noted.